Welcome to the deep dive. If you are a machine learning engineer or a data scientist or even a quantitative researcher, you are probably intimately familiar with this overwhelming temptation to treat literally every complex problem as a nail.
Oh, absolutely. And a massive overparameterized neural network is always the hammer.
Exactly. I mean, the prevailing wisdom these days often dictates that you should just throw this absolute mountain of data at a black box architecture, minimize some generic error metric, and just trust the optimizer to somehow reverse engineer the underlying physics of the environment.
Right. And that brute force approach has just become pervasive across the industry. We see it constantly, particularly when researchers try to bridge deep learning with quantitative finance.
Yeah, just dumping raw price data into huge architectures and expecting trading signals or, reliable risk metrics to just pop out.
Exactly. But the moment you step into the rigorous world of modern portfolio theory, and specifically the domain of covariance estimation and risk minimization, that brute force hammer just completely shatters.
It really does, because suddenly you are dealing with this highly noisy, non-stationary environment. And in this space, black boxes, well, they tend to just memorize historical noise. They completely fall apart when you deploy them out of sample.
They do. So our mission today is to systematically break down a highly innovative paper that entirely flips the script on these traditional neural network portfolio optimizers.
Yeah, the paper is titled End-to-End Large Portfolio Optimization for Variance Minimization with Neural Networks Through Covariance Cleaning. Quite a mouthful, but a really fascinating piece of work.
It really is. The authors essentially built the antithesis of a black box. You can really think of it as a glass
The
box.
glass box, right? I love that term.
Because instead of treating the network as this opaque oracle that predicts a covariance matrix to be fed into a standard convex optimizer later on, they took the exact analytical symmetries of the global minimum variance portfolio, the GMV, and hard-coded them directly into the architecture.
So it's a rotation-invariant, dimension-agnostic neural network, and, if you are building models that actually need to scale, the practical takeaway here is pretty striking.
Yeah, it trains on a small, randomized basket of maybe 50 to 350 stocks.
Right. But then during inference, without undergoing any retraining or structural adjustment at all, it can execute on a universe of 1,000 stocks.
Which is incredible, and it actively beats state-of-the-art estimators like quadratic inverse shrinkage or QIS, and even those really complex dynamic conditional correlation models.
And it doesn't just do this on paper, right? It does this within a highly realistic, friction-heavy simulator. But, I mean, how do you even begin to hard-code mathematical symmetries like permutation equivariance into a neural network without just crippling its ability to learn?
Well, to understand why this specific mathematically constrained architecture is so necessary, we first have to establish the baseline bottleneck.
Core mathematical problem.
Exactly. We need to talk about why traditional covariance matrix estimation fails so spectacularly in high dimensions. If you are optimizing a portfolio, your out-of-sample risk inflation is heavily governed by the aspect ratio.
Which we call dollars. And that's simply the number of assets divided by the number of time observations, the delta tin.
Right. So under standard assumptions, as dollars approaches 1, meaning you have roughly as many assets in your portfolio as you have days of historical returns, the sample covariance matrix becomes severely ill-conditioned.
Yeah, because the sample covariance matrix is your standard maximum likelihood estimator. So the smaller eigenvalues of that matrix, they just cluster dangerously close to zero.
And the critical thing here is that they aren't near zero because of some fundamental market truth. They're near zero purely because of sampling noise.
Right. And when you construct a GMV portfolio, the optimization math actually requires you to invert that covariance matrix.
Yes. And inverting a matrix with near zero eigenvalues causes those tiny noise-driven values to absolutely explode. They dominate the entire output.
So you end up with portfolio weights that are massively over-allocating to mathematical noise
Right.
rather than the true underlying signal.
Exactly. Now, the immediate statistical reflex for any data scientist listening to this might be, well, just increase the denominator.
Right. Feed the model a longer look-back window. If you have 500 assets, just, give the model 5,000 days of data to push Delalshers closer to zero and stabilize the matrix.
But that intuition leads straight into what we call the stationarity trap. Financial time series data is strictly non-stationary. By naively extending the historical window, you inevitably start mixing highly heterogeneous market regimes.
Yeah, you end up blending the dynamics of a low volatility bull market with the sheer panic of a liquidity crisis from 5 years ago.
Precisely. You introduce severe structural bias. You simply cannot feed a neural network a decade of historical market data and expect it to magically extract the current forward-looking correlation structure.
Right, because increasing the time window is mathematically self-defeating, so you have to filter or regularize the covariance matrix you currently have.
And the traditional solution in quant finance has been rotation-invariant estimators, or RAEs. The most famous example probably being Ledoit-Wolff nonlinear shrinkage.
Yeah, Ledoit-Wolff. These estimators essentially adjust the sample eigenvalues to account for the noise, but intentionally retain the empirical eigenvectors.
They do. RAEs are foundational, but the authors of this paper highlight a really critical flaw in how they are traditionally optimized in machine learning contexts.
Right, because methods like Ledoit-Wolff optimize for the mean squared error. They specifically minimize the Frobenius norm against the true unseen population covariance matrix.
Exactly. But minimizing the Frobenius distance between two matrices does not necessarily minimize the realized out-of-sample variance of the resulting portfolio.
Okay, I have to pause here and emphasize the mathematical friction because this is exactly where the paper pivots. If the Frobenius norm is the wrong target metric, how do you mathematically train a neural network to minimize portfolio variance?
That is the big question.
Because if you just set your loss function to, minimize variance, how does the network do that without outputting a matrix that completely loses its positive definite guarantees?
Right, because a traditional pipeline separates the prediction of the matrix from the portfolio solver.
Exactly. So if we are doing this end-to-end, what exactly is the target?
Well, that realization dictated the entire architecture. Because the Frobenius norm is suboptimal for this specific task, the authors had to build a network where the loss function is the actual realized out-of-sample variance of the portfolio itself.
The out-of-sample variance.
Yes. And to achieve that, they had to make the entire GMV analytical pipeline completely differentiable.
So they train directly on the financial outcome. I think the loss function they use is multiplied by the realized portfolio variance. So it's non-dollar times dollars transpose times the out-of-sample covariance matrix times dollars.
Exactly. And multiplying by nano, there's a really vital engineering detail.
Oh, because it scales the objective.
Yes. It ensures the magnitude of the loss remains stable, regardless of the cross-sectional dimension. Whether your batch has 50 assets or 500 assets, the gradients don't explode or vanish during backpropagation.
That makes total sense. So to make this end-to-end differentiable while guaranteeing a valid, positive, definite covariance matrix, the network basically splits the raw return data into a 3-module pipeline.
Right, a pipeline that directly mimics the analytical formula of the GMV.
So first, we have a lag transformation module that applies temporal weighting. Second, there's a multivariate denoising block that cleans the correlation structure. And third, a feed-forward module that estimates the inverse marginal volatilities.
And this modular separation is where the dimension-agnostic breakthrough actually happens. Because the trainable parameters in these modules are shared across assets and across eigenvalue ranks, the model's total parameter count is entirely decoupled from the number of assets, one and down.
I have to admit, when I first read the paper, this specific part really tripped me up. Let's actually explore the mechanics of this extrapolation. So the model is trained on random subsets of 50 to 350 assets. But during inference, they just dump 1,000 assets into it. How can a model mathematically survive being fed a covariance structure of 1,000 assets when it has literally never seen a matrix larger than 350 by 350 during its entire training phase? Doesn't the dimension mismatch just crash the network?
Well, to understand the extrapolation, we need to dive deep into the operations inside those 3 learnable modules. We really have to look at how they enforce mathematical symmetries locally, which inherently allows them to generalize globally.
Okay, let's look at Module 1, the lag transformation, which handles the temporal weighting. Usually, quantitative models just impose a fixed exponential decay for past returns, right?
Exactly. Think of the standard risk metrics approach. Recent days matter more, past days decay exponentially towards 0.
But this network does something different. Instead of imposing a rigid equation, it learns a flexible, element-wise differentiable curve.
It transforms the raw return using a hyperbolic tangent function. Specifically, it scales the return by a learned parameter, passes it through the hyperbolic tangent, and scales the output by another learned parameter.
Right, so the network dynamically learns 2 variables via backpropagation. There's a scale factor, which we can call alpha, and a clipping factor, beta.
And the empirical finding from this module is fascinating. When they analyzed what alpha actually learned over time, it did not learn an exponential decay.
It learned a power law decay, right? Roughly at a rate of t to the negative 0.2f, which means, given total freedom to optimize for minimal variance, the neural network prefers a hyperbolic weighted moving average over the traditional exponential decay.
Yes. The underlying market data itself is basically proving that market memory decays with heavy tails, not exponentially. Shocks from the past linger in the covariance structure much longer than an exponential curve would ever suggest.
Wow. And then you have the beta factor, which controls the saturation of the hyperbolic tangent. Over time, beta fits a saturating exponential curve.
Right. Think of this beta module like a dynamic shock absorber for the data. For very recent returns, the beta parameter is small, meaning the mapping is nearly linear.
So the network is looking closely at the actual magnitude of the recent returns. It's essentially calculating a continuous Spearman correlation.
Exactly. But for data from, say, a year ago, beta is large. It aggressively clips outliers until the historical data is essentially binary.
It just stops caring about the magnitude of a move a year ago and just looks at the sign of the return. Was it positive or negative?
Yes, and that aggressive clipping perfectly aligns with the mathematical definition of a phi coefficient, which is a measure of association for two binary variables.
That's brilliant. So the network dynamically shifts its correlation metric from a continuous magnitude assessment for recent data to a robust binary phi coefficient for distant data. It's such a smart way to filter out historical noise.
It really is. But the true engine of this architecture is Module 2, the eigenvalue cleaning.
The multivariate denoising block. This is where we replace traditional statistical methods like the Lidwat-Péchet estimator, right? The network has to take the empirical eigenvalues generated from the first module and map them to cleaned eigenvalues.
And crucially, this mathematical function must be permutation equivariant.
Yeah.
The ordering in which you feed the assets into the model absolutely should not change the underlying covariance structure.
Right. And the authors pull directly from random matrix theory here, specifically using the Coulomb gas formulation.
Yeah, for listeners who might need a quick refresher on RMT, the Coulomb gas formulation essentially treats these sample eigenvalues not as static numbers on a page, but as physically repelling point charges trapped in a potential well.
So the required shift of any given sample eigenvalue to its clean state depends mostly on its local neighbors like local repulsion forces and a coarse-grained global mean field force acting from the rest of the spectrum. But wait, if we need permutation equivariance and we need to process a sequence of interacting elements that exert forces on each other, my immediate machine learning reflex is to reach for a transformer.
Oh, of course.
Right. Why not use self-attention or deep sets? Computing pairwise interactions across a sequence is basically the absolute standard playbook for modern sequence modeling.
It is. But the authors explicitly address why attention is actually the wrong tool for this specific physics problem. Pure attention architectures compute independent pairwise interactions. To capture higher order, collective dependencies in a dense cluster of eigenvalues, you are forced to stack as many attention layers as the maximum local interaction order.
And as Run say, moving from the 350 assets in training to 1,000 assets in inference, the spectral density just drastically increases. You are cramming 1,000 repelling particles into the exact same potential well.
Exactly. As that spectral region becomes denser, an attention network requires an impossible depth to capture the collective repelling forces. If you try to run that, you immediately hit vanishing gradients and a massive computational explosion. It fundamentally cannot scale to unseen dimensions.
So to solve this, the authors utilize a bidirectional long short-term memory network, a BIL-STM, and they use the sorted eigenvalue rank as a pseudo-time coordinate.
Yes. Think of the BIL-STM here like a physical comb running through a tangled head of hair. It scans the ordered eigenvalues sequentially from the smallest to the largest and then backward from the largest to the smallest.
So as it moves step by step through the sequence, it is feeling the knots, the local repulsions between neighboring eigenvalues, and smoothing them out, while still maintaining an awareness of the overall shape of the spectrum.
Right. The hidden states of the BIL-STM perfectly capture that local repulsion as short-term memory and the global mean field confinement as long-term memory. And it accomplishes this entire physics simulation with only about 34,000 parameters.
That's incredibly lightweight.
Because a recurrent neural network applies the exact same transition weights at every single sequence step, It mathematically does not care if the sequence has 300 eigenvalues or 1,000 eigenvalues.
It's learning the fundamental physics of the eigenvalue repulsion, not memorizing the dimensions of a specific matrix. I mean, that is just a masterclass in architectural alignment.
It really is beautiful.
Hmm.
And finally, we have Module 3, marginal volatility, which completes the matrix.
Right, and this module is much more straightforward by comparison, isn't it? It's just a simple three-layer, multi-layer perceptron.
It is. It takes the individual sample standard deviations and maps them to output inverse marginal volatilities. Empirically, it learns to flatten the left tail of the volatility distribution, meaning it slightly reduces the influence of extremely low volatility assets.
While heavily inflating the right tail, which effectively increases the penalty on highly volatile assets. So, you take the transformed time lags from Module 1, the perfectly clean eigenvalues from the Bill STM in Module 2, and the scaled volatilities from Module 3, and you recombine them to output the final inverse covariance matrix.
That's the end-to-end process.
But, an elegant mathematical architecture is absolutely meaningless in quantitative finance if it just gets destroyed by transaction costs and market slippage.
Let's transition from theory to reality. We need to look at the rigorous out-of-sample backtesting they ran from 2000 to 2024.
Because the ultimate test of any portfolio optimization model is friction. The authors first established a baseline with a frictionless setup, allowing unconstrained long-short positions.
And in this idealized environment, the neural network achieved a Sharpe ratio of 1.91. To put that in perspective for the field, the state-of-the-art QIS estimator achieved 0.94, and an average Oracle estimator hit 0.91.
But there is a massive reality check hiding in that frictionless test. The neural network achieved that 1.01 Sharpe ratio with a turnover rate of 112% every 5 days.
112%. Yes. And a gross leverage of 3.07. If you attempt to deploy that strategy in the real world, prime broker fees, margin requirements, and slippage will basically eat your alpha for breakfast on the very first day.
Exactly. And the authors fully acknowledged that limitation. Consequently, they built a high-friction, highly realistic simulator. They constrain the portfolio to long only by taking the neural network's learned inverse covariance matrix and passing it into an external quadratic programming optimizer.
Right. If you've ever tried to deploy a statistical arbitrage strategy, you've probably faced the exact wall this simulator is designed to emulate.
Oh, yeah. They dropped the optimizer into a continuous calendar interactive broker simulator. And this is not a toy model. It calculates margin excess dynamically. It applies tiered interest rates on cash balances. It deducts FINRA and SEC regulatory fees.
And crucially, it models execution price risk based on actual closing auctions. There is no assumed perfect VWAP execution here. It models the harsh reality of market orders.
And this simulator is where the true extrapolation test occurs. They deployed the model on the top 1,000 capitalization stocks. This represents an aspect ratio of roughly 0.83.
Which is wildly outside its training range, which remember was constrained between 0.04 and 0.29.
And despite the friction and the massive dimension scaling, the neural network still completely dominates. It achieves a 1.058 Sharpe ratio, a 12.6% annualized return, and it delivers the lowest short-term variance of any model tested, hitting exactly 9.0%.
It beats the average Oracle, it beats power mapping, it beats QIS, and it outperforms incredibly complex dynamic conditional correlation models.
The underlying mechanics of how it achieves this are fascinating. When you analyze the constraints, the model generates alpha entirely through extreme risk reduction.
Right.
But I have to point out the most shocking statistic from the simulator results, the turnover. The neural network achieves this market dominance despite maintaining a 57% turnover rate every 5 days in the long-only setup.
Yeah, that's incredibly high.
Usually, a 57% turnover rate in a high-friction simulator is an immediate death sentence for a strategy. How does it mathematically survive that drag?
It survives because the allocations are so mathematically optimal. The risk reduction is so incredibly precise that it actively prevents the massive drawdowns that usually compound negatively over time.
So it's protecting the downside that fiercely.
Yes. The model sizes its position so efficiently that the rebalancing trades capture microscopic mean reversions, and the generated alpha completely absorbs the massive friction costs.
Wow. The temporal performance is also a really critical validation point here. We see so many machine learning models in finance perform beautifully in backtests prior to 2010, only to degrade completely in modern, hyper-efficient markets.
All the time. But this neural network's performance actually gets better over time. It distinctly pulls away from the competing benchmark models, specifically after 2012.
Which proves definitively that it is not just overfitting to distant, inefficient historical regimes.
Exactly. By aligning the geometry of the neural network with the specific geometry of the financial problem, the authors essentially solved the scaling and stationarity issues that have plagued the field for a decade. It actively minimizes realized variance, rather than just fitting a Frobenius norm against an unseen population matrix.
It is genuinely a masterclass in using deep learning not as a blunt instrument, but as a scalpel guided by mathematical theory. But, to wrap up our deep dive today, I want to leave you with a forward-looking thought, building directly on a limitation the authors themselves admit.
Right, because the current model isn't perfect.
Exactly. Right now, this model is strictly rotation-invariant. That means it cleans the eigenvalues beautifully via the Bill STM, but it leaves the noisy empirical eigenvectors completely untouched.
It fundamentally assumes the sample eigenbasis is the best baseline we have, and only adjusts the magnitude of the risk along those specific axes.
But consider what happens if the next evolution of this architecture breaks rotational invariance. Imagine coupling this Bill STM with a clustering base module that explicitly denoises the eigenvectors themselves, maybe adjusting them based on shifting market regimes or hierarchical sector structure.
Oh, that would be wild.
Right. How much lower could the out-of-sample variance drop if the network was allowed to actually reshape the underlying geometry of the risk modes themselves? We started today discussing the danger of treating every problem like a nail and using neural networks as a black box hammer.
And this research proves that if you take the time to build a glass box, if you explicitly hard-code the mathematical symmetries of your domain into the architecture, you don't just get a model that learns faster.
You get a model that understands the physics of the data well enough to extrapolate into dimensions it has literally never even seen.